All right, let's just dive right into it. Welcome to this Forge College Explainer, part of our Solidity from Zero track. Today, we're drafting the actual blueprints for efficient event monitoring. Now, in our previous lesson, we hashed out the mechanics of listening to events off-chain, right? We talked about setting up subscriptions, pulling historical data, all that good stuff. But today, we're flipping the script entirely. We're going to engineer exactly what those smart contracts should be publishing in the first place. Honestly, think of it like designing a nuclear control panel. If you build the interface wrong, the poor guy trying to monitor it off-chain is going to have a very, very bad time. So here are the blueprints we're sketching out today. We'll cover the off-chain connection, the oversharer versus the minimalist, the canonical key pattern, how to keep secrets off-chain, mapping out event-driven architectures, and finally, your concrete takeaways. Let's get to work. Section 1, the off-chain connection. Just to bridge the gap from our last lesson really quick, you already know how to subscribe to a node and filter data off-chain using WebSockets and polling. But listen, those off-chain listener behaviors, they're completely at the mercy of the events your contract emits. Think about it. What exactly should a contract publish so your off-chain monitors aren't going bankrupt or constantly breaking? If you just dump every single piece of transaction context into an event, you're creating a bloated, super expensive mess. But if you design it right, your filtered results become incredibly stable, dirt cheap to query, and super easy for off-chain tooling to actually digest. Moving on to Section 2, the oversharer versus the minimalist. Let's look at two totally different types of smart contracts for a basic marketplace sale. On the left, we have the oversharer, sale verbose. This guy tells you every unnecessary detail. 4 parameters, 3 index topics, and a massive string of metadata attached directly to it. Every time this fires, it's writing these huge JSON blobs on-chain that inflates the transaction receipt, crushes the emitter with gas costs, and makes historical backfills a total nightmare. Now look at the minimalist engineer on the right, sale minimal. Just 2 parameters, 1 index sale ID and a tiny numeric payload. It's lean, it's clean, and it makes event filtering incredibly cheap. Now I want to zero in on that indexed part for a second. You are strictly limited to a maximum of 3 indexed parameters per event in Solidity. 3. That is it. When you index a parameter, it becomes a topic in the log entry. That's what lets peers and RPC nodes filter logs using Bloom filters, which is basically a super fast mathematical search trick, without scanning the whole data payload. Because you only get 3, you've got to treat them like absolute gold. If you waste them, your off-chain monitors are going to have to download entire blocks just to find what they're looking for. But hey, gas fees and filtering speed aren't our only headaches, right? The blockchain itself is pure chaos. So how do we survive a chain reorg without our off-chain database having a complete panic attack? When the blockchain changes its mind and reorgs, your listeners might see events magically disappear, reappear, or even duplicate. If we don't have a specific mechanism to deduplicate these things, our off-chain state is going to get totally corrupted. Which brings us to Section 3, the canonical key pattern. Let's see how this solves the whole chaotic reorg problem. A canonical key is honestly just a unique indexed identifier for a specific operation. Think of it as an operation ID that keeps going up, or a unique hash for every single meaningful action. By stamping this explicit operation ID onto every emitted event, your off-chain listeners can just check their database for the last seen ID. If a reorg happens and they see an event with an ID they've already processed, they're like, oh, already got this one, and they know exactly how to handle it. It makes deduplication deterministic and totally stress-free. All right, Section 4, keeping secrets off-chain. We've got to talk about privacy. The blockchain is a public ledger. Anyone can read it. So we absolutely do not want to publish sensitive plaintext memos or private user data directly on-chain. Instead of leaking secrets and pumping up log sizes with giant text strings, we keep the actual payload off-chain. What we put to the event is just a lightweight memo hash or a pointer, like an IPFS URI or a SHA-256 digest. This is a total game changer. The event just taps the listener on the shoulder to say something happened and points to where the heavy, private data actually lives. So the golden rule here? Just avoid raw strings in your events whenever you possibly can. Swap out that bulky string memo for a super clean, highly efficient bytes32 memo hash. It keeps the on-chain log tiny, prevents accidental leaks, and because it's a cryptographic hash, authorized viewers can still perfectly verify the data integrity off-chain. You get all the security for literally a fraction of the cost. Next up, Section 5, event-driven architecture patterns. Designing events isn't just throwing a line of Solidity code at the wall. It's about engineering the entire workflow between your contract and your consumers. Check out this patent-style breakdown of the exact event shapes you should be using. First, the canonical ID pattern. Emit an ID, an actor, and a data hash. Listeners use that ID to deduplicate and backfill efficiently. Then, the pointer plus payload pattern. Emit an ID and a payload hash. Listeners see that and know, okay, time to download the heavy payload from IPFS or an S3 bucket, which saves crazy amounts of bandwidth. Finally, the state change pattern. Instead of emitting some fleeting action, you emit the new state. Listeners map that directly to their local state machines, so they don't have to constantly hit your contract with queries. Honestly, if you follow these 3 mechanical steps, your system is going to be practically bulletproof. Step 1. Always emit an indexed canonical key. Step 2. Persist your large or sensitive payloads off-chain. Step 3. On the listener's side, maintain idempotent handlers keyed by that canonical key. And by the way, idempotent just means if your handler gets the exact same message twice, like from a chain retry, it doesn't process it twice. It just safely ignores the duplicate and your database stays perfectly intact. Finally, Section 6, Takeaways and Next Steps. Let's run through the final checklist before you build your next monitoring system. Adopt these minimalist blueprints. 1. Prioritize searchable keys like operation ID so listeners can actually filter your data. 2. Ruthlessly balance your indexed versus non-indexed parameters. Remember, you only get 3. 3. Keep the chain clean by pushing large content off-chain via pointers. 4. Design events to show clear state change semantics, not just random backend details. And 5. Build those idempotent, checkpointed workflows off-chain. Do this, and long-term analytics becomes an absolute breeze. So, here's a thought to leave you with. Does every single meaningful event in your current smart contract have a searchable, canonical key? Seriously, use that question to audit your own code today. Look for those massive string memos and replace them with a clean hash. I really hope this explainer gave you the blueprints you need to write leaner, smarter events. Be sure to visit forge.college to learn more about this and to catch our next lesson, using filtered event data, where we're actually going to implement these listeners. Thanks so much for joining me on this Forge College Explainer, and I'll catch you in the next one.